Hello students, the purpose of this video is to discuss inverse functions. So what exactly is an inverse function? For a function and its inverse, the values of x and y are interchanged. This lets us know that the domain of the function is going to be the same as the range of its inverse. That means when I look at the x values of my original function, they are going to be in the y values of my inverse. So just to give you a visual for my visual learners, if my original function has an xy table and my x's are 1, 2, 3, then in the inverse function, those x values of 1, 2, 3 are going to actually appear in the y column as 1, 2, 3. So my x values become my y values in the inverse. So what exactly does the inverse do? Well, the cool thing about the inverse is that it should give us back the original value. So kind of unrelated to math, but you start out with something, okay? Maybe I start out with an apple and I perform an operation, some function on it, and it creates a banana. Well, what happens is when I have that new thing, I've turned the apple into a banana, if I go and do the inverse to the banana, it's going to bring me back to my original value, which is the apple. So think about what you know about inverses already. You're familiar with inverse operations like addition and subtraction and multiplication and division. All those operations are familiar to you, and you know that addition and subtraction, for example, are inverses of one another. So if I start out with no M&Ms and I add 3, now I have 3 M&Ms. And if I perform the inverse, which is subtract 3, I get 0 M&Ms, which is what I originally started back with. So again, performing an operation and then performing the inverse brings you back to what you originally start with. So we've learned about something called the composition of functions. When we compose a function and its inverse, the result is the input value. So basically, we're undoing everything to get back x. So again, when I had 0 M&Ms and I added 3, I undid it by subtracting 3, which was the inverse, to bring me back to having 0 M&Ms. So there is some notation that we're going to use, and that is this little f to the negative 1. We don't ever really read that as a negative 1 power. We just read that as f inverse. But essentially, what we're going to be doing is the composite of two functions together. And we're going to see, does f composite g of x equal x? And then we're going to actually go backwards as well. We're going to do g composite f of x. And we're going to see, does that get us x as well? And as long as when we do those compositions, we get x in both scenarios, then we're good to go. And we know that they are, in fact, inverses of one another. So again, for notation purposes, we're going to represent the inverse by saying f inverse of y. Again, this is function notation for representing a function that is the inverse. Now, will I always have an inverse? Absolutely not. It must be a function that is one-to-one. Now, if you recall back many sections ago, we learned about the vertical line test. And the vertical line test was used to determine, do we have a function? And the concept was draw a vertical line, hit the function only one time, and you're good to go. It is a function, meaning there were no repeating x values. Well, if you pass the vertical line test, you can then test for something called one-to-one, which essentially means there are not only no repeating x values, but there are also no repeating y values. So we're going to utilize something called the horizontal line test. If you're able to draw a horizontal line so that it hits the graph in more than one spot, it's not one-to-one. But if I can draw a horizontal line, hit my function only one time, then we are good to go and we can say that the function is one-to-one. So we're going to actually end up doing this graphically. So we're going to think about the function, and in this case the parent function x cubed, which we know makes the disco graph. And if I draw a bunch of horizontal lines, I only hit the function one time and therefore can conclude that it does have an inverse function. Now the definition of an inverse function. So we just discussed that in order for an inverse g to be true for any given function f, I should be able to compose f into g into f, and both of those give me back x. So determine whether the following are inverses of one another. So I'm going to begin by looking for f composite g of x which hopefully you recall is the same thing as saying f of g of x. And so I'm going to take my f function because that is the outside function. I'm going to say 100 plus 12x. But in for x, I'm going to plug in the g function, which is x minus 100 all divided by 12. But because I know a 12 here and a 12 on the bottom, I know that those cancel each other out, so that I am left with 100 plus x minus 100. And the 100s end up canceling out, and I'm left with just x. So that's great. That's what I want to end up with. So f composite g of x worked. It got me what I was looking for. So that's good news. So now I'm going to check g composite f of x. I'm going to do the same thing and hope that it also gives me x. So this is the same thing as g of f of x. And again, because g is my outside function, I'm going to utilize that function first. So x minus 100 all divided by 12. And in for x, I'm going to plug in my f function, 100 plus 12x. And 100 minus 100 go away. And so I am left with 12x divided by 12. And the 12 on top and on bottom cancel each other out. And again, I am left with just x. So that means g composite f of x also worked and got me the value x. Therefore, yes, these are inverses. These are inverses. So that means I could notate this as this is my f of x and this is my f inverse of x. Because I've now identified that yes, they are in fact inverses of one another. Now another way you can be asked the question is to actually find the inverse of an equation. So a second ago we were verifying that things were inverses of one another, but now I actually want you to find the inverse of an equation. So there's 4 steps. You're going to replace f of x with y. You'll change out your x's and y's, meaning every x will become a y and every y will become an x. You'll solve for y, and you'll write the final answer in inverse notation. So for example, find an equation for the inverse function of f of x equals 3x minus 1. So step 1 says to replace f of x with y, so y equals 3x minus 1. Step 2 says make every y into an x and every x into a y. Step 3 says go ahead and solve for y. So x plus 1 is equal to 3y. And then that's x plus 1 all divided by 3 is equal to y. And then step 4 says write your final equation in inverse notation. X plus 1 all over 3. And that would represent your final inverse function. So 4 pretty easy, simple steps. Looking at another one that's written in fraction form, we're going to do the same thing. So we'll start out with step 1. We're going to rewrite the problem as y is equal to 3 minus x all over x plus 3. Step 2, we're going to change our y's to x's and all of our x's to y's. Now in step 3, because my function is a fraction, I'm going to actually multiply out the denominator. Because if I multiply out the denominator, it gets rid of the fraction, which helps me out significantly. But if I do that to one side, I have to multiply to the other side as well. So that means I'm left with y plus 3 times x is equal to 3 minus y. And I'll go ahead and simplify. And I want to get everything that has a y on one side. So that has a y and this has a y. So I want those on one side and everything else on the other. So I'll keep the xy and I'll add the y to the other side. I'll keep the 3 and I'll subtract the 3x. And then I want to isolate y. And I notice that I have a y in both terms. So I can go ahead and take that out as a GCF. which then allows me to divide out the x plus 1. So that I can then go write my final inverse function of 3 minus 3x all over x plus 1. Okay. Alrighty, as always, I hope you found this video helpful. If you have any questions or concerns, please don't hesitate to reach out and ask, and I hope you all have a wonderful rest of your day.